Okay, so here's another problem. Oh, my arrow. What happened to my arrow? Let's draw that in right there. Okay, beautiful. All right, so ammonia is produced from the reaction of nitrogen and hydrogen according to the following balanced equation. Okay, so this one was a little bit nicer because there's already a balanced equation. And just kind of confirming really quick, I see 2 nitrogens on this side and 2 nitrogens on this side and 6 hydrogens on this side and 2 times 3, 6 hydrogens on that side. Beautiful. Okay, so now the problem is asking me, what is the maximum mass of ammonia that can be produced from a mixture of 1.00 times 10 to the 3 grams of nitrogen, that's 1,000, and 5.00 times 10 to the 2 grams of hydrogen, that's 500. And so remember, I'm going to do one problem. We'll call the hydrogen number 1, where I try to figure out how much mass that's going to create. And then I'm going to do a second calculation, number 2, where I figure out how much ammonia I can make from that amount of nitrogen gas. Okay? Hopefully I left myself enough room. It looks like I did not. So let's go for it. Okay, so let's do number 1. I'm going to try to write a little bit smaller than I normally do. So I'm starting with the first number that I have. You know, that's why I draw this arrow, right? This arrow helps me visualize the calculation I need to do. I'm going to start with this number, and it's going to spit out that number. Okay, so I can say 5.00 times 10 to the 2 grams of H2. And grams of H2, I need to convert that into moles of H2 because mole is how I compare things in a chemical reaction. And let's see here. The periodic table tells me it's 2.016 grams of hydrogen in 1 mole. Okay. So from this balanced reaction, it tells me 3 moles of hydrogen make 2 moles of ammonia. All right. So we'll say 3 moles of H2 makes 2 moles of NH3. And don't forget to cancel out those units as you are going. At least that's what I like to do. It helps me check that I'm on the right path. And then now finally I'm at moles of NH3, but I need to be at grams of NH3, right? So I know I can say mole NH3 per gram NH3. And from that last problem, right, we calculated that it was 17.02 grams of NH3. Okay, so let's do that calculation. So 500 times 10 to the 2, I can enter in this calculator by saying 500 E2, oops, not that way. I go 5.00 E2, and look, it tells me 500, okay? That's what it's supposed to be. So 500 times 1 times 2 times 17.02. So 500 times 1 is 500, times 2 is 1,000, times 17.02 is this number, and then divide by 2.016 equals, and then divide by 3 equals. And I get, yes, so the way this calculator works, that's 2,814, okay? And with, so I want to write all that down, 2,814, and I want to do only 3 sig figs. So this is where I'm going to use scientific notation, and I'm going to say 1, 2, 3, okay? So that's 2.81, but I'm not going to write 814. I'm just going to write 2.81 because that gives me my 3 significant digits times 10 to the 3rd power. Okay, and that's grams of NH3. Okay, so now let's do number 2. Let's calculate it for, so we started with the hydrogen, now let's start with the nitrogen. Okay, so now we're going to say 1.00 times 10 to the 3 grams of nitrogen. And I know I need to go moles of nitrogen Oops. Nope, I don't need to do that. I need to stick with the same unit, right? If I have grams of nitrogen up top, I need to have grams of nitrogen on the bottom. Then moles of nitrogen on the top. And I know from my table that it's 28.00 grams of nitrogen in 1 mole of nitrogen. And then now I'm at moles of nitrogen, and I can see in my balanced reaction, 1 mole of nitrogen makes 2 moles of ammonia. So mole of nitrogen to mole of ammonia. 2 moles of nitrogen makes 1 mole of ammonia. And then finally, this very last line I can copy identically from above because it's the same conversion, moles of nitrogen to grams of nitrogen. Okay, and my units cancel all very nicely. And so let's calculate this out. Okay, so I can write 1,000 on this calculator by saying 1 point, I'll just put the zeros in just to be complete, 1.00 e to the 3, and I'm just going to say equals, yep, that's 1,000, times 1 times 1 times 17.02. So times 17.02 equals, and then now divide by 28.000, right? And then divide by 2. And I get a number that I did not get in my notes. Oh, you know why? I know what I did wrong. Haha, those of you that are watching are probably like screaming at your computer screen like, no, no, no. 1 mole of nitrogen makes 2 moles of NH3. Geez, Harmon. Okay, let's make sure that everything else looks good. Okay, now let's try it. So we know 1 times 10 to the 3 is 1,000 times 2 times 17.02 equals, okay, and then now divide by 28. Divide by 28.00. Okay, that's the number I have in my notes. And so, okay, I'm going to write that down as 1,216. I'll round it up to 216, but I still need 3 sig figs out of this. And so right here's where my comma is. So that's going to go 1, 2, 3. Okay, we'll make that like a very clear comma. So now that's 1.2 something times 10 to the 3. And for 3 sig figs, it's 1.2, and then that 6 is going to make that 1 round up to another 2. Okay, grams of NH3. So what is the maximum amount that can be created? Remember, the least is the most. So 1.22 times 10 to the 3, that's 1,220, or 1,216 with 4 sig figs grams of ammonia. Okay. Now it says what mass of which starting material would remain unreacted. So what that means is which one is in excess? Which one do I have leftovers from? Okay? And so it's going to be the hydrogen. And the way that I know it's got to be the hydrogen is because, look, the hydrogen could possibly make a lot more ammonia than the nitrogen did. So that means nitrogen is limiting. I'm just going to write this down for my own clarity. And hydrogen is in excess. So that's what we're going to have leftovers of, hydrogen. Okay. So how do I calculate which starting material will remain unreacted? Okay, this is a little tricky. So what we need to do is actually work backwards. We're going to start with this number, 1.22 times 10 to the 3 grams of NH3. We're going to start with this number that I just calculated. And now we're going to say, okay, well, how much of this would need to be, let me think about how to say this. Okay. So we're working backwards now, and I'm going to call that number 3. Sorry, it's getting all crunched together. Okay. So we're going to say if I have 1.22 times 10 to the 3 grams of ammonia. How much hydrogen did I need to have made that in the first place? Okay, think about that. So that's kind of like saying, if I want to make 10 ham and cheese sandwiches, how much ham would have I needed in the first place, right? So we're just doing, it's no different than that, right? Just think of this as cooking. If I want to make 17 ham and cheese sandwiches for Gordon Ramsay, how much cheese would I have needed in the first place? Okay, so that's what we're doing here, right? So 1.22 times 10 to the 3 grams of ammonia is the maximum I could make. So now we're just going to work backwards, folks. We're going to say grams of ammonia to moles of ammonia. Remember, don't forget the dimensional analysis process. Down, up, down, up, down, up. We know that that's 17.02 grams of ammonia in 1 mole. Okay? And then now I'm working backwards. I'm working from ammonia to hydrogen. Okay? So I need to have mole of NH3 here and mole of hydrogen here. And my balanced reaction tells me 2 moles of NH3 can be made from 3 moles of hydrogen. Okay, let's make sure that we're canceling units correctly. Okay, good. And then now finally I need to go moles of hydrogen to grams of hydrogen, because that's what we're trying to get to, right? We're trying to say what mass would be left over. And so we know 1 mole of hydrogen is 2.016 grams of hydrogen. Okay, so what do I get when I do that calculation? All right, so I can say 1.22 times 10 to the 3 equals, so that's that first number. I'm going to say times 1 times 3 times 2.016. So times 1 is the same number. So times 3 equals times 2.016 equals. And now I'm going to say divide by 17.02 equals. And then now I'm going to say divide by 2 equals. And yes, that's the number that I'm supposed to get. Okay. And so that's 216.7 something or other. 3 sig figs would make this 217. 217 grams of hydrogen. So what does that number mean? That number means if I wanted to make 1.22 times 10 to the 3 grams of ammonia, I only needed 217 grams of hydrogen. How much did I have in the first place? I had 5.00 times 10 to the 2. That's 500 with 3 sig figs. So I'm going to write that as 500 point grams of hydrogen. But now it's saying that I only needed 217. So what mass of which starting material would remain? Well, I'm just going to subtract it now. 217 grams minus 500 grams gives me 283 grams of H2 left over. Okay? So, and just again, to walk you through this in the simplest way, right? We could do the exact same thing here, right? If I had 12 slices of cheese, how many could I have made? If I had 6 buns, how many could I make? If I had 15 slices of ham, how many could I make? Okay? So from all of this, we learned that we could only make 5 slices of ham and cheese, right? So how much cheese would I have left over? Well, hopefully you can see pretty easily that's going to be 7. But how do I get that? Okay, well, I can work backwards and say, I know 5 ham and cheese sandwiches is made from just 1 slice of cheese, which tells me I need 5 slices of cheese. And if I had 12 slices of cheese up here, minus 5 slices of cheese, then I have 7 slices of cheese left over, right? So you can see with this simple algebra, you might think, or with these simple numbers, you might convince yourself you don't need to do this dimensional analysis stoichiometry thing because it just makes it confusing. Well, this dimensional analysis stoichiometry thing actually makes it a little bit easier. It helps you guide your way through. Okay? So make sure that you're okay with doing a problem like this. We're going to get some practice doing a problem like this in lecture. Okay? So I'm going to keep going with this.